Now we're recording. Okay, so um, now as a reminder, of assignments being due on Tuesday, homework 2 from section 2.1. That is due tonight. We should have some time because this week we're covering section 2.2 spread across the 2 days. So I expect we'll have some time toward the end, or I can make some time for any questions that anyone has on that assignment. Now I noticed that not many people ever turned in homework 1 on MATLAB. Granted, I've already said there's no consequence for turning in late, and now I'm curious as to how many people want to take advantage of that to turn it in by the end of a semester, which technically I've allowed. I'm not sure if that's in your best interest, but let's just see how that one plays out. But my leniency on lateness applies only to that assignment. Just to make sure we're absolutely clear on that. Okay. And also, a few people have turned in the Canvas quiz for 2.1. So remember, each assignment from now on, except for MATLAB 1, includes both. There's the problems from book and the associated Canvas quiz. Okay. All right. Now, it seems that based on my experience from the last time I taught this class, well, actually, it's true of every time I taught this class. It's been about 10 times. That this section on computer arithmetic and floating point numbers tends to be even more of a pain than most of the other sections, perhaps because it's more computer sciencey. So after a miserable experience from 2017, I cut out a lot of the homework problems. So the homework for 2.2, originally it said all of the problems in this section, and that would have made all of you want to kill me. So it's just these 8 problems and the Canvas quiz. Okay. All right. Okay. So what this is about is something that on paper comes quite naturally to you. Well, maybe not as naturally to students nowadays as back in my generation. Good old-fashioned arithmetic. And now we have students using a calculator to figure out 2 squared. It's a little depressing. But since everyone's relying on calculators to do their arithmetic anyway, that's the subject of this week. How do computers do arithmetic? And also, what are the issues involved? Which will be a focus on Thursday. So the first thing I have to talk about for today is how are numbers even represented on a computer? And I could give a very short answer to that question, which I'll then expand on. Basically, it's scientific notation, but in binary, so base 2. So my explanation about representation of numbers, floating point representation, is really going to start with something that you're familiar with, scientific notation, and I'll start with examples in base 10, and then work my way to base 2. Because it makes sense that computers work in binary, base 2, because you have 0 corresponding to off and 1 corresponding to on. So from an electrical hardware point of view, it makes perfect sense. Although I'd read that long ago, I think in the 60s or so, in Russia, they had a computer that worked in base 3. I'm not sure how that would go electrically, like off, kind of on, and on. I really don't know, but I just know that base 3 happened, but obviously it didn't take because we're still in base 2. So describe a floating point number in any base, which I'll refer to as beta, has this form. So x is our number. So we have a sign, positive or negative, and then we have a number m, and then the exponent, the base raised to an exponent. So all of these parts, so we have a sign bit, 0 corresponding to positive, 1 corresponding to negative. So we only need 1 bit to represent that, obviously, since there are only 2 values possible. And then we have m is called the mantissa. Now, the informal definition of a mantissa, it's where all the significant digits go. And then we have the base beta, as I mentioned, and the exponent e. So you can see how this essentially corresponds to scientific notation. So I'll give some examples. Dang it. Sorry, this thing is failing to cooperate again. Okay. So here's some examples. Start with the same number, 117. So in decimal, so that's beta equal 10. So it's expressed in scientific notation. So it's plus 1.17 times 10 squared. So we have, so the mantissa is 1.17. And I'm going to write that in terms of fractions involving, or where all the denominators are powers of 10. So we have 1. So I'm going to flesh out each digit and the role that it plays in building up a mantissa. So we have a digit to the, so we really only have 1 digit to the left of a decimal point. Of course, I'm going to call it a decimal point even when I'm working in binary, but whatever. So we have, so whatever digit, we have 1 digit allowed to the left of a decimal point, regardless of what base you're in. And then for digits to the right of a decimal point, I'm going to have 1 times 10 to the minus 1 plus 7 times 10 to the minus 2. So in the mantissa, it's a sum of your digits divided by powers of 10. So the only possible mantissas you can have are, you can think of it as linear combinations of negative powers of, or I should say non-positive powers of your base. Okay. And you'll see what this means when I go to another example involving binary. So it's really the number shifted so that you only have 1 digit to the left of a decimal point. And then finally, the exponent, e, is just going to be 2. All right. Now, same number, but in binary. All right, so x is going to be positive, and I have, as a fraction, to be 117 over 64 times 10 not 10, but 2 to the 6. Now 64 is 2 to the 6. Now the reason why I chose 2 to the 6 is because the number 117 is sandwiched between 2 to the 6 and 2 to the 7th. So between these powers of 2, so 64 and 128. Just as in decimal, 117 is between 10 squared, which is 100, and 10 cubed, which is 1,000. So because it falls in that range, that the lower value indicates the exponent. So now I'm going to write this again in binary digits. So that would be 1.11011 times 2 to the 6. Okay. So now I need to decode that for you. Now, and the thing is, in decimal, we take this for granted. It's so natural to us. So it can still be difficult to adjust to interpreting numbers in any other base. So if we think about what we have with decimal case, 1.17. So that digit to the left is just as is because it's multiplied by 1. And then we take the other digits and multiply them by negative powers of 10. So 10 to the minus 1, 10 to the minus 2. Here, same thing, except it's with base 2. So mantissa, which is 1.11011, equals, so 1 plus, so its first digit, it's going to be a 1, so it's going to be 1/2. And the second digit, it's a 1, that corresponds to the 2 to the minus 2 place, so that's 1/4. Then we have nothing here in the 1/8 place, which would be the 1/1000th place in decimal. Third digit is going to be corresponds to 1 over the cube of your base, whatever your base is. Then we move to the 4th place. So we have a 1 in that position, so we'll have 1/16. Then nothing in this place, which is a 1 over 2 to the 5th place. And then this digit in the 1 over 2 to the 6th place. So we have all of these added together. And if we were to combine these fractions by putting everything over a common denominator, which would be 64, that would be 117 over 64. Okay. Right. So there's a LaTeX error here that I need to fix. Okay. All right, so this is how we can interpret the mantissa when it's expressed as in binary. So whatever digits we have, or at least the ones digit, because 0 or 1 is all we can have, is multiplied by the appropriate negative power of 2. So 2 to the minus 1, 2 to the minus 2, and so forth. In fact, I'll reflect that in here. So this is 2 squared, 2 to the 4th, 2 to the 6th. That's 2 to the 6th. All right, so questions about the layout of a binary number.
How did you know that x would equal positive 1.1101?
So first, before I answer that, I'll emphasize that I do an example for this in the book, but I decided not to put the related problems in the homework. But how you would do it is, so given any number, if I just give you 117 or whatever out of the blue and say, okay, go ahead and express this in binary. The first thing you would do is you want to know the exponent. So in general, the exponent is equal to the floor of the log in whatever base you have of the absolute value of that number. In other words, take the absolute value, take a logarithm to that base, and round down. So in this case, if I go to MATLAB, make that a little bigger, or a lot bigger. All right, so if I take the log 2, so log 2 in MATLAB does log to base 2 of 117, so I get 6.87. So that means that my exponent is going to be 6. So then what you do, whoops. To get to mantissa, first so let y equal x over base to the exponent. So now, where'd it go? Okay. So now, so that so now your number y that you're going to work with to get your mantissa, or actually, I don't need to call it y. It is a mantissa. Because the mantissa in general is going to satisfy. Actually, I need to put that there. So it's going to be something that's strictly less than the base. And so, for example, in decimal, I'm only allowed one digit to the left of a decimal point. So if I make that digit as large as possible, I have 9. So I can have 9.9999, whatever. Point is still going to be less than 10. So whatever you have for your mantissa is definitely going to be less than your base. So then what you can do is... Okay. So basically keep dividing and taking a remainder. And so that's how you get your digits. So, for example, if I have, okay, all right. Or another way of putting it, actually, this explanation would be better. Okay. All right. So the first digit so the integer part of m is the first digit. So for example, 117 over 64, that's going to be a number that is greater than 1. That's 1 point something. So that'll give me a 1. Then subtract that, multiply by the base to move next digit to left of decimal point. Yeah. So for example, 117 over 64, is that. So then I subtract 1 from that. Okay. So now, yes, and we have a 1 again.
You subtract off 1 again.
Yes. Yeah, and what will happen is, if I do this again, subtract 1, multiply by 2 again, we get another 1. But then watch what happens. I subtract 1. Well, what will happen at some 0? Yeah. So every time I multiply by 2, whatever you get to the left is your digit. So I have a long drawn-out example on page 62. where I do this with, and the number in that case is e. So I convert that to binary up to a certain point. Okay. So the general representation of a floating point number in whatever base so x is equal to plus or minus, and then I have, for mantissa, I have d0, point, d1, d2, dot, 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 and then, whoops, p minus 1. So I have a grand total of p digits times my base to the exponent, where p is the precision. Now there's basically 4 numbers that characterize a floating point system. The first, whose importance has already been made obvious, is the base, beta. The second number is the precision, so that is the number of digits. Oops, I don't want all that bold. That's the number of digits into the mantissa. So in other words, total number of significant digits you can have in whatever base. And the exponent has to be between these 2 limits, L and U. So we have a lower limit and upper limit on the exponent. Generally, the lower limit will be negative, because you want to be able to express the numbers that are less than 1. You want to be able to express very small numbers. And then U describes what large numbers you can represent.
You said L will be less than 0 or less than or negative number?
Oh, well, now negative numbers are accounted for by the sign bit.
Right. You said L will be 0.
Oh, no. L itself would be negative. Like, you want to be able to express something like 10 to the minus 15. So you need negative exponents for that purpose. All right, so these 4 properties of a floating point system, base, precision, and then the 2 limits on the exponents, those define the characteristics of your floating point number system. Okay. All right, so this is a general representation of a floating point number. All right, so the major characteristics of floating point system come from a base, the precision, and the 2 limits on the exponent. Now, it doesn't tell you everything about the floating point system, but I'll get to those other properties in just a moment. Okay. Okay. Let's make sure I'm not accidentally skipping a page. Okay. All right. So the fact that we can have limits on the exponents, where'd everything else go? Okay. Actually, I'm going to move this. No, I'm not. I can start filling cut it here. Underflow and overflow. You need to talk about those because that gets into how small or how large numbers are you allowed to have. Okay, so underflow is when numbers get too small to be represented. And then overflow when they're too large. Now, one of these is a much bigger problem than the other. Because if a number turns out to be so small that it can't even represent it in a floating point system, it's not a really big deal for computational purposes. You can say, oh, that's approximately 0. So you basically just declare it to be 0. But But when it gets too large, you don't have an easy out like that. So it's considered basically infinite. And that actually the IEEE floating point system, which I'll get to in a little bit, actually has certain numbers that are set aside to be interpreted as plus or minus infinity. Okay. So how large or small can numbers get? So I can actually give formulas for those. So the underflow level. Okay. Actually, I can talk about overflow first. That's easier to discuss. The overflow level is going to be beta. I shall call this OFL, which is short for overflow level. So it's beta raised to the u plus 1 times 1 minus beta to the minus p. Okay. Now, why is that? Because I already said that u is the largest exponent you're allowed to have. But I'm going to rewrite this number as beta to the u times beta minus beta to the minus p minus 1. Okay. Whoops, that should be a superscript, not a subscript. Okay. Now, so I mentioned, if we look at the general floating point number above, this part, beta to the e, is what goes here. Now set the exponent equal to the largest one that's allowed. So that's u. For the rest of this, everything in parentheses here, that's the mantissa. And I already said that mantissas are always less than the base. So you take the base and you subtract off the smallest amount that you can. So in other words, you subtract off 1 in the very last digit of a mantissa. So in decimal, I can describe what that is. So the largest mantissa in decimal is equal to 9.999 for however many digits that you have. So total of p digits. Because p digits are what you're allowed. So if your precision in this example is 9 digits, then that's the largest mantissa you're allowed to have. Okay. Whereas in binary, it would be 1.11111. So think of it this way: 1 plus 1/2 plus 1/4 plus 1/8, etc. That is a geometric progression. So if you use your Cal 3, you find that if you go on infinitely, that would sum up to 2. It's like the bar joke about mathematicians. You have infinitely many mathematicians walk into a bar. So the first one goes up and orders a beer. And then the second one orders half a beer. The next one orders a fourth of a beer, and so on and so on. So then the bartender just puts 2 beers in the counter and says, "You guys got to know your limits." Sorry, not sorry. Okay. All right. So any number larger than this is going to be is going to overflow. So in the IEEE floating point system, the upper limit for exponents is 1023. And I'll explain when I talk about IEEE in detail where that number comes from. So if I go over to MATLAB and I do, and this is binary, so 2 to the 1023, so that's allowed. So if I go one step further, let's see if it'll let me. No, it doesn't. So one place higher, it's infinite. And I could also have minus infinity, of course. Okay. Now, the absolute largest, so a formula I had here, if I use this, if I have MATLAB compute this is going to be 2 to the 1024 out here. And it won't do that. It'll call that infinite. But if I express it this way, then it will let me do it. So the value of P in MATLAB is, in IEEE is 53. Okay, so U equals 53. I'll fill in all the parameters. L equals minus 1022, and P is equal to 53. So if I do 2 minus 2 to the minus 52, if I multiply that by 2 to the 1023, it should give me a number. Now, I am setting myself up for embarrassment here, but oh well. 2 to 1023, which we saw was allowed, but now I want to make it a little bigger, times 2 to the minus 2 to the minus 52. Okay, so this number is allowed. So that is absolutely as large as I can get. So if I make this mantissa the slightest bit bigger, this would be 2 to the 1024, it'd overflow. In fact, here I'm subtracting off a very small number. Suppose I subtract off a number that's a little smaller still. Infinite. So I really did hit the absolute limit. Okay. So questions about overflow level.
Why is it exactly 1023? Because I know, like, in most computer stuff, 1024 makes up megabytes, gigabytes. And so forth.
When I can explain the bit layouts, you'll see.
Okay.
Yeah. All right. So that's overflow. What about underflow? So in that case, the underflow level is equal to the smallest mantissa that you can have times beta to the smallest allowed exponent. But the smallest mantissa is not so clear cut, because it depends on whether numbers are normalized. Okay, so that's what I'm going to talk about next. So once I get to that point, then I'll be able to say, okay, here's what the underflow level really is. For instance, in IEEE. So what does it mean for a floating point number to be normalized? So the definition is quite a simple one. A floating... dang it. I'll just send this to a new page. Okay. Floating point number is normalized if the first digit of mantissa, the only digit to the left of a decimal point, is required to be non-zero. So examples. Normalized would be like 3.14. Not normalized would be like 0.00314. So here, the leading digit of mantissa, the one to the left of a decimal point, is 0. So that is not a normalized number. So why do we have normalizing? So there's a pro and a con to normalizing numbers. The pro is that each number has a unique representation. Because if I don't require normalizing, I could have a 1-bit sequence that would give the number in this form. Actually, I'm going to put an exponent in here. No, I want a LaTeX command, not an actual backslash. Stop it. God, this program hates me. Times 10 to the minus 4. So that way, so here we have the same number in both cases. 3.14 times 10 to the minus 4. So if we say that numbers must be normalized, each number has a unique representation. Because otherwise you could have different mantissas, different exponents that have the same value. But the problem with that is smallest mantissa equals 1, so can't represent as many smaller numbers as you can if you do not require normalization. So explain what that means. So the underflow level with normalization equals base to the smallest allowed exponent, because the mantissa has to be greater than or equal to 1. By contrast, underflow level without normalization is going to be equal to the base to the L minus P plus 1. Okay, because now you can have beta to the 1 minus P as that is your smallest mantissa. So that corresponds to mantissa being 0.0001, where the total number of digits is P, your precision. So you said all digits 0, you just have a 1 in the last last digit, no matter what your base is. That is the smallest allowed mantissa. So if you don't normalize, the numbers you're allowed to represent can get a lot smaller. So what's done in IEEE? IEEE system actually does both. So a compromise is called gradual underflow, which means that numbers are generally normalized unless the exponent is equal to that lower limit. So in that case, and only that situation, numbers are now not normalized, thus allowing smaller numbers to be represented. Okay. Now, okay. Other properties of a floating point system. Rounding convention. Like, okay, long ago, maybe elementary school or whatever, when you were taught how to round numbers, what were you taught? Here's the same as what I was taught. Then you round up. So for instance, 0.5, you would round up to 1. Okay, otherwise you round down. Okay. So here are certain conventions for rounding. So there's chopping. So you always round down. So whatever decimal part you need to toss out, just get rid of it. No digits are changed. And then, so in other words, you truncate the base beta, I keep typing beat, beta expansion after P digits. So your mantissa is allowed to have P digits Any digits after that, gone. Okay. Then there's rounding. So you round to nearest number with at most p digits. So this is how we're all taught to round. But what about breaking ties? Because the way we're taught to break a tie is if a number is equidistant from two numbers that can be represented. So example, let's suppose we have, let's say we only have 4 digits allowed. So if p equals 4, and let's suppose that x is, okay, so let's make a number with, okay. So that number has 5 significant digits, but I'm only allowed 4, so I have to round. So I'm going to make this last digit a 5. Must round. So we're taught to round. Actually, I'm going to change the example a little bit to make it more interesting. Let's see. I'm going to make that a 6. Okay. So we're taught to round to... So suppose I want to round this in such a way that I only have 4 significant digits rather than 5. So what would that be? So in other words, the last digit has to go. Yeah, 4.987. Okay. But computers generally, like IEEE actually does not do that. So it's better to round to 4.986, round down, based on this convention, round to even. So we break ties by ensuring last digit is even. So that causes a round down in this case. You get 4.986. Now, that seems like a bit cumbersome. That now you're checking this last digit to see if it's going to be odd or even after you round. To reduce bias. So the way we're taught to round, so when you have that, or always rounding up when you have a choice is statistically biased. So by allowing the possibility of rounding up or down based on criteria that whatever digit, last digit, which could be anything, is making sure it's even. That's a less biased method of rounding. So it's still rounding. It's just that with rounding you can choose many different conventions for breaking ties. So this is one that's preferable. Okay. So questions about that? All right. Now yet another essential property of a floating point system is called machine precision. Now there's different definitions. So machine precision, which is just noted by a bold U, also known as unit roundoff, which is probably why the letter U is chosen to represent it, is the largest relative error in representing any real number. So in other words, okay, so I have, if we have, so we have this inequality where FL of x is the floating point representation of x. So x can be any real number whatsoever, like pi, something has infinitely many decimal digits, or infinitely many digits in any base. So FL of x is whatever number we get after we round. So we've tossed all but the most significant p digits, and that is our floating point representation of x. So if there's going to be some error involved, so the relative error is going to be at most this number u. So it's the error incurred, relative error incurred due to rounding. So I can actually give a value of for u. Okay. So we have is equal to the base to the 1 minus p if chopping is used. And what, because this is the value of the last digit of a mantissa. So if your mantissa is 0.00001, that's this value here. It's the base raised to the smallest power, the most negative power that can be used in a mantissa. If you're rounding, then you can cut that relative error in half. Regardless of what a rounding convention used, if rounding is used. So that's one key reason why we prefer rounding instead of chopping. Chopping is very simplistic, easy to implement. But we can represent numbers more accurately if we round. Okay. All right. So in IEEE, beta is 2, p is 53. So we have 2 to the minus 53, and that is 1.1 times 10 to the minus 16th. So this is the error, relative error incurred at most when we represent a floating point number in the IEEE system. Okay. Okay, I want to check if I assigned this problem. No, I did not. Now, another notion of roundoff error that's actually it's similar to this, but it's not exactly the same, is it's the smallest number you can add to 1 and still get something greater than 1. So other definition, and I want to emphasize non-equivalent. U is smallest number such that floating point representation of 1 plus BFU of 1 plus U is greater than 1. Because if U is really, really tiny, once you round, you have exactly 1. So then FL of this number would be equal to 1. So that would be too small to be unit round-off. Okay. And the funny thing is, so in IEEE, this is 2 to the minus 52. So I can show you this in MATLAB. If I have 1 plus 2 to the minus 52, it gives me 1.00000. But if I do 1 plus 2 to the minus 53, it just says it's 1. So here there actually is something past the decimal point. Here there's not. Okay. But this value is still the largest relative error you can have from rounding in this system. All right, so now I can tell you about the IEEE floating point standard. So these are the numbers you actually work with. So for double precision, that's what we'll focus on. There's single precision and floating, and single precision and double precision. It's 8 bytes, which is 64 bits. So that's all you got. You just got to make that work to represent your significant digits, and also allow for a wide range of magnitudes, so you can have large and small numbers. So how are these 64 bits apportioned? So we have one sign bit, then we have 11 bits for the exponent, and then 52 bits for the mantissa, resulting in precision of 53. Now, there's one kind of strange thing here, because I said P, 53, is the number of digits you're allowed to have in a mantissa. But there's only storage for 52. So how is it that we're able to have 53 bits in our mantissa when you're only allowed to store 52? Here's why. Numbers are, like I said, are generally normalized. So first digit of mantissa is non-zero. But we're in binary, so what must that digit be? 1. You know it's 1. So why store it? You're wasting space. So I could say not just non-zero is 1, so no need to store it. So really, the storage that we have at 52 bits is all the digits that are to the right of the decimal or binary point. The 1 that's to the left of that point is implied. Okay. Now, I'm going to, okay. As far as the number, the 11 bits for the exponent, if we have 2 to the 11th, that is equal to 2048. So if I have 11 bits, and my exponent's going to be an integer, I can represent 2048 integers. So you would think that we would have these exponents, minus 1023 less than or equal to exponent is less than or equal to 1024. Because that is a total of 2048 values. So 0 up to 1024 is 1025, and you add on the negatives, you get 2048 digits numbers altogether. But it's not. Because so exponents minus 1023 and 1024 are reserved. They cannot be used for representing actual numbers. They're reserved for special numbers like infinity, also NaN, which is short for not a number. Okay. So your exponents can only go from minus 1022 to 1023. And then if your exponent is minus 1022, you switch to that denormalized mode. Okay. Now, what I'm going to do is, in MATLAB, I'm going to show you, it turns out we can actually inspect the representation of a floating point number. And yeah, I realize I should be, I'll save this I don't have diary going, but I'll save this text for you. So I'll just copy and paste after class. Okay, so floating point representation. So I can let x equal I'll just pick one with pi, let's say. And I've shown you this format before, but I didn't talk about it because back then it would not have made any sense. Format hex. So now we look at x, and we have this. So I'm going to show you what this means. It looks pretty random. So these are hexadecimal digits. So 0 through 9, and then A through F to give a numbers 10 through 15. Because hexadecimal is base 16. So we need 16 digits altogether, 0 through 15. So we use letters for that. Now, hexadecimal is nice because it's difficult to convert decimal to binary. But it's very easy to convert hexadecimal to binary because one hex digit is 4 binary digits. So if I look at these 16 hex digits here, so in binary, what I have is, so the 4 in binary is 0, 1, 0, 0. Because I have 2 to the 0, 2 to the first, 2 squared, 2 cubed. So the only thing I have is 2 squared, which is 4. And then I have, so every group of 4 digits that I type is one hex digit. Okay, so the next ones are 0, and then I have 9, which is 1, 0, 0, 1, because that's 8 plus 1. And then I have 2, so we only have 2 to the first. And then I have 1, so that's 0, 0, 0, 1. And then F, that's 15, so that's 1, 1, 1, 1. 8 plus 4 plus 2 plus 1 equals 15. And then B is 11, so it's 8, 2, 1, etc. So I'm not going to go further. All right. So 4, 0, 0, 9, 2, 1, FB. So I've translated this part of a number into binary. Because now I can explain to you what the binary digits mean. First bit, sign bit. 0 for 1, 0 for positive, 1 for negative. So x is positive, so the sign bit is 0. The next 11 bits, which is 1 through 0, 0, 0, 0, are the shifted exponent. So what I'm going to do is I need to figure out what this number is in decimal. Well, this is 2 to the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 0, 0, 0, 0, 0, 0, 0 in binary equals 2 to the 10th, which is 1024. Okay. So what you do, bless you. Now that is not the exponent. To get the exponent, subtract 1023. So the exponent equals 1. So from this representation, if you write out the first 3 of these hex digits in binary, discard the first one, because that's just a sign bit, and you take the rest. So remember, these going from right to left, 2 to the 0, 2 to the 1, 2 squared, 2 cubed, etc., all the way up to 2 to the 10. So for remaining digits, our mantissa, after the point, a decimal point or binary point or whatever you want to call it. So a mantissa is equal to 1 point, and then I have these digits that follow. So I'm just going to do the first few, like the 1001. Okay. And dot, dot, dot to indicate the rest. So if I work out what this number is, so value of mantissa is equal to 1 plus this next number, which is 1/2. And then what would be the next non-zero contribution to the mantissa, based on what I have here? 1/16. Okay, so if I do common denominator, that's 16. That's 25 over 16. So if I take 25 over 16 as my approximate mantissa times 2 to my exponent, which is 1. Actually, I can put disp here. I don't want this to scroll up too much. Oh, sorry. Whoops, I'm still in format hex. I want format short. All right, so 3.12. But that's because I cut it off after only these digits. There's still a whole lot more that need to be included. Okay, okay, so this gives you an idea as to how numbers are represented internally. That we have so sign bit, exponent, and then everything else is what goes into the mantissa. Actually, how far do I did this, and then that. So the next one, 16, 32, 64, 128. So I've gone a little bit further. So 25 over 16, and I add on the next non-zero digit, 1 over 128. Okay, closer to pi anyway. At least it rounds up to 3.141, but yeah, I still need to include more binary digits to get this closer to pi. Now, if I go back to format hex, now, if I do 1 over 0, that's going to be infinity. And now we look at the exponent. Okay, so if I do format short, and 1 over 0, yeah, so it calls that infinity. So here's representation. So the digits is equal to, so 7 is 0, 1, 1, 1, so 4 plus 2 plus 1, and then all ones after that. So in other words, this is the largest allowed exponent that you can have. So the exponent, after you deduct a 1023, is equal to 1024. Not allowed to be used as an exponent for actually representing numbers. So this special reserve value exponent is for infinity. Okay. So that number is 2 to the 11th minus 1, which is 2047, minus 1023 is 1024. So, but again, it can't be used as an actual exponent. Another special number, 0 over 0. Not a number. So if you ever see this, NaN, chances are it's because you did 0 over 0 somewhere. Because 0 over 0 is what's called an indeterminate form. There are other indeterminate forms that we learn about. Like infinity minus infinity is an indeterminate form, for example. So we just can't ascribe a value to it, even an infinite one. So what does that look like internally? Oh, someone just submitted a quiz. I'll look at it later. So here we have, instead of 7FF, it's FFF8. So the bits are equal to 1111, 1111, 1111, and then I have another 1, or 0100, etc. So the first bit corresponds to a sign bit that's negative, but we're not really using that. And then, again, all the exponent bits are 1. So same exponent value of 1024, but we have different, so what IEEE does is use a mantissa for error codes. Basically error reporting when you have invalid numbers. So it sets aside certain numbers for its purpose. Now, another one, 0. All 0, which is what you'd expect. The funny thing is, it's very important that if we insist on normalizing all numbers in all circumstances, you actually can't represent 0 because the mantissa has to be greater or equal to 1. If you denormalize, then it now makes sense for all bits being 0 to have a value of 0. So that's another key aspect of this gradual underflow, that we at least denormalize some of the time. But the funny thing is, 0 actually has two representations. I can do -0. So now we have, actually that one, okay. So that is going to be, actually I goofed up here. I should have 1, 0, 0, 0 up here. So the bits are equal to 1, and then 0's after that. So the sign bit is set to 1. So if you denormalize numbers, not only are you able to represent 0, you actually have two representations of 0. 0 and -0. Not confusing at all. Okay. Okay. So to summarize, so the central characteristics. So P equals 53, and we have L equals -1022, U equals 1023, and certainly, of course, the base is 2. All right. Now, by contrast, single precision, you only have 4 bytes, so 32 bits. So you have 1 sign bit, 8 bits for the exponent, and then 23 bits for mantissa. So P equals 24 in that case. So single precision. So base is base 2, 24, and then the exponent. So it's going to be, so 11 gives you 10, so 8 gives you 7, minus 126, and the upper level exponent is, actually, yeah, 127. Okay. So that's going to be 4 bytes. Okay. All right. So what are you going? So this is all the new material I'm going to cover today. On Thursday, I'll be talking about issues that arise from floating point arithmetic, particularly with this kind of floating point system. A lot of things can go wrong, actually. But I want to use the rest of the time if anyone has any homework questions. Yes?
2.1.9.
9?
Yeah.
Okay. Okay.
Okay, so I'm a little confused on the second line. To suppose that.
Okay.
What are we exactly supposed to do with that within the formula for relative forward error?
Okay. So all you're going to do is you figure out the relative. You get your relative condition number, and then you're just going to multiply that by 10 to the minus 2. And that will give you your estimate, like the upper bound for the relative forward error. That's for this part of a problem. And as far as the confirmation goes, what you would do is, so if x naught is 2, you need to find x naught hat so that this relative error is equal to 10 to the minus 2. So in other words, you're adding plus or minus 1% to 2 and trying out those values in these functions to actually get an actual value for forward error to compare to your estimate.
Okay, so since x naught is equal to 2, then x hat naught would be equal to the 10 to the negative 2?
Well, remember, it's a relative thing. If it was absolute backward error, it would be 2 plus or minus 0.01. But it's relative.
So we just choose a value for...
Well, no, it still satisfy this with an equality.
It'd be 5 thousandths. You divide the 100
Wait, 5.
by
Not.
by 2. You
Wait.
divide 101 by 2.
No. Actually, there's another problem that illustrates. Okay, where'd it go? Okay. So if you put 2 here, and r is your relative error, so you're taking 2 and multiplying it by 1.01, or 1 minus 0.01. Either way, that would so the value you get here would be would have that amount of relative error. Yeah. Okay. Sarah, did you have a question? Because I saw a grimace there.
I guess
I
on,
have a question.
Oh, what?
on the subject of submitting it, one file in the email, that's it.
That'll work, yeah. I mean, and yeah, for me, it doesn't care if it's multiple files or one file, but yeah, there isn't really much in the way of MATLAB in this one. So, yeah, so you can either send scans of handwritten pages, or if you do it in a document, you can do that too. I really don't care. Is there a question? Yeah.
2.1.5.
5. Okay.
So I know to do your forward error, you do your y approximation minus y. And since we're using 1 minus x squared over 2, so y hat,
Yes.
we're going to take that, subtract the cosine of x, which are all y.
Yeah.
So do we plug in pi over 4 for x and all those and solve? Is that
Yeah. So you're just checking this out at x equals pi over 4.
and then we would divide it by the cosine of pi over 4 here relative.
Yes. Yeah. Divide by the
Square
exact.
root of 2. Okay.
Yep.
But the one other thing I was confused on was I know that x is pi over 4 when I was trying to do my backwards error, but I was trying to figure out my x approximation. I did a little.
Oh, okay.
Just take pi and divide it by 4 with your calculator and use that as your approximation, or
Oh, okay. So to get backward error, so this is where you assume that the. Actually, going to type this up here. Yeah, there's an inverse involved.
do the inverse. Okay.
Yeah.
So do the inverse.
So
Of
okay, so 2.1.5 to get backward error.
like this.
Use the fact that f of hat x is equal to
I gotta take the inverse of all that.
hat f of x, meaning that cosine of, and so in this problem, cosine of x hat is equal to p2 of x, or p4. So in other words, everything in this is known except x hat. You can solve this equation for x hat. Okay.
In 2.1.12,
Okay.
when you look at the limit as h approaches 0,
Okay.
of the
Probably gonna let people write.
are you just putting, like, do you just substitute 0 in, like, do you just evaluate the limit? Or
Okay. Not right away.
not right away?
Okay, so let me make sure I'm thinking of the right problem. Okay. Where'd it go? Okay. Yeah, so I got a few questions about this one. Because if you did plug in h equals 0, you would get 1 as a limit, but I've given you a limit. To get to rate of convergence, what you do, okay, I'll type this into the notes also. You must substitute Taylor series for e to the h, then simplify as much as possible. Because what you will find when you make that substitution, it's going to be a big old cancellation fest. So, which terms are left standing? And then that'll tell you the rate of convergence.
So what happens if it's submitted?
Sorry, what?
What happens if someone has submitted and maybe it is an error? Is the assignment?
Oh, okay. So, for instance, if it's already been turned in,
Yeah.
go ahead and update it. I mean, because at least it's been turned in, so don't worry about that. I mean, if someone wants to change your whole assignment, it might be a different story. But like a pinpoint correction, I'm not going to worry about that. Go ahead and actually, well, as far as a procedural point, if there's a update to a submission, like you've turned it in well before the due date, and then you find you want to fix something, I would prefer just a complete reset. Like change whatever file within that you need to change, and resend the whole thing, because that way I'm not trying to figure out, okay, where does this go within what you already sent me. So it is less thinking on my part. Okay, we still have some time. Are there any other homework questions from up here or down there?
Okay, so with number 12, with the Taylor series,
Yep.
how many terms do we, I guess when we start expanding it, though,
Until you get something that doesn't cancel.
okay.
Yeah, like if you use too few terms, you get 0.
No, but do we need remainder?
Well, the thing is, remainder happens at whatever point you choose to cut off. But for this problem, you wouldn't really need to remainder. If you could write out like a whole bunch of terms and ... and then certain terms will cancel, and then the first one that's left is the rate of convergence. And you're only trying to express it as a power. Like the answer is going to be order h to some power. And whatever constant's in front of it doesn't matter. Yes, I mean, yes, you don't need to explicitly write out the remainder term for this problem. The actual remainder does play a role in here. Because you're trying to get the constant.
So you said we should plug in the Taylor series for all h's or just e to the
Just e to the h, because when your expression is a polynomial, that's when it's very easy to get to rate of convergence. So any part of it that is not a polynomial, only the e to the h, that's what gets replaced. All right. Any other questions?
Can you go back to the numbers?
Go back to what?
Which is
Okay. I sense there are no more questions. Is there anyone who needs anything else left up on my screen for note-taking purposes? Of course, I'll post all this stuff. Okay, then.
That's why I said.
Well, no, you're not multiplying it by. Right.
yeah.
Would that be 0 again?
How was your birthday?
Oh, it's nice. Yeah.
So for the Taylor series expansion, when you're evaluating it, it's f of x or f of a plus the first derivative of it times x minus a.
Yeah.
So like your a, is it just going to be like what is the a?
Is A equal to X?
Well, in this problem, it's going to be 0 because you're trying to see what happens around 0.
It's h basically. Yeah.
Well,
or
x is h.
Oh, so
A is 0.
that means it'd be e
okay.
to the 0 power right here.
Yeah.
Oh.
Okay.
And that'd be 1.
Yes.
And then, so that'd be derivative of 1, right?
Well, the
no.
derivative of e to the h, plug in 0.
Yeah. Plug in 0, so it'd be
To
e to the
A.
0 would be 1, right?
Yeah.
So the derivative of 1.
Yeah. Well, no, derivative,
of e to the x evaluated at 0.
yes, which is 1.
Yeah.
E to the 0 evaluated, like that?
Well, yeah, you only took, you take derivative, e to the h is e to the h.
Right.
Yeah, to differentiate first.
Differentiate first, then
Then
plug
plug
in
in.
0.
Yes.
I'm
Okay.
sorry. And then, but right here, so this would just be x minus 0, which is x. So
But x is,
let me think for just a minute. So whenever you said take derivative of e to, I'm saying e to the x because that's what I've always worked
Okay,
with.
yeah.
So that would be e to the x, and then I'll plug in the 0, make it 1,
yes.
and it'd be 1 times x, which is x.
But x is, in this problem, x is,
Oh, cosine of the 4. So then I mean pi over 4, right?
oh,
No, I'm in a different problem.
Yeah.
I know.
exponential.
X.
But x is h.
Oh yeah, I understand. I was going to go back
Oh.
and convert them to h's.
Oh, okay. All
I'm
right.
sorry.
Okay.
But 1 plus h. I know. I was going to go back and
Yeah,
put in
yeah.
h's, and then I'll do it again,
Yes.
and just keep doing that until
Until something
I
doesn't
get to-
cancel.
till something does not cancel.
Yep.
Gotcha. Because I may get to a point where I'll have because I may have a minus 1 and minus x, and then all that's canceling.
Yep.
Then I'll start getting things that don't cancel.
Right.
Okay. So whenever you had talked about, whenever I had h and h squared, if I would have just looked at it as e to the 0 power is 1 and not done a Taylor expansion, I'd have tried to say it was an order of h.
Right.
And that's not what I'm going to end up
Right.
getting.
Yep.
Okay. All right. Well, I'm going to work on see what we get. Okay.
Okay, I wanted to clarify on the one where you're finding the relative condition number, and it's the one with 10 to the negative 2.
Yeah.
So, because I did it wrong, I found the relative forward error and then the relative backward error, and I didn't find the condition number. But
Oh, okay. Interesting.
but because that's basically, I just need to go back and I just need to look at it. I have questions, but I don't know what they are. I'll look at it and then I'll probably send you my questions.
Okay, I'll be ready.
Okay.
Okay.
Thanks. Oh, I just need to get out of this building.
Yeah.